All right, looks like ready to get started. So everybody, I'm Sam Modernock. I'm a project engineer at the Foundry 4.0 Center at the University of Northern Iowa. I do a lot of the robotic programming we do and testing and usage of robots for finishing and processing of castings. Today, I'm just going to run through some of what I have set up for this workshop and kind of the structure of what we're going to be looking into for casting finishing. So just to start out, minimize this. All right. Just starting out. So casting, finishing. At the University of Northern Iowa, we are branching into looking into how we're going to do the finishing process as quickly as possible for as many parts as possible. So some of the stuff we've started to get into and been exploring for quite a while now has been into the realm of offline programming and how we're using sensors and other equipment to optimize our programming process and make things as quick and easy as possible. Here you'll see kind of a slash by example of one of the pieces of equipment we use when we're doing robotic finishing. But we can't use these different methods of using offline programming just to get a good idea of how a program is going to look and also to speed up that program process with some of the built-in things you can make while you're doing offline programming. Just a quick recap of kind of how this workshops are going to go over the next 4 weeks here. This one right now, we are just going to get started with how we're going to install our software and how we're going to set up our cell. So if you're following along doing some of this example with me, you'll have a few of the pieces that we'll be getting into later to set up an example cell and how this process works, at least for this offline programming program that you should have downloaded if you received the message. But beyond that, we'll also be then going to the future sessions, looking into some of the basics of how we can use a robot to perform finishing in the two different fashions, part to process and process to part. And that's either the robot is going to hold a part and bring it to a piece of equipment to do some sort of operation, or the robot is going to hold a tool and bring that to a part to do some sort of finishing operations. And then we're going to wrap it up on the final day, showing you some of the practical examples, how you're going to try and translate some of this offline programming to your robot. Working with the software we're using for this demonstration, it's made a generic offline programming language for many different robot brands, but are several other options available, even including ones from the robot-specific brands. At the University of Northern Iowa, we handle a few different brands of robot, from Kukas to Kawasaki to ABB to Fanuc. So we use a offline programming software that can be used for a variety of robots, not necessarily the brand specific one. But beyond that, for today, we're going to be breaking down into, first of all, getting your software set up to be able to run this, and then kind of working in how you're going to have to set up your robot in your offline programming space. So a lot of the things with robotics is getting a solid foundation, getting your safety equipment in place, and knowing where everything's going to be, and then start going from there to steadily increase the complexity of the parts you're making and of the programs you're going to be making. And so today we're just going to start going through some of that setup and then some of the quick programs we can make just to get our robot ready. This is stuff that we can also build into the robot itself, but we can also build into our offline programming and have that ready to roll for whenever we're using the cell. All right, so a quick thing. So the files needed, if you receive my email, you'll have your step files of our part we're going to be working on, as well as an .rdk file for the cell itself. This is what we're going to be opening in Robotic. So that is the offline programming software that we'll be using. And we should have access to the features we'll need to show you some of the programming steps you'll need to take, and as well as the settings file. That'll just make things easier. We'll be able to download our settings and get going right away. First thing, hopefully you already have it installed from the email, but if you have Robotic installed, it'll be come preloaded with a program called VS Codium. They use that natively as their Python editor, and it should come prepackaged. if you want to now, you can scroll to find this program. We'll be using it just once here to get all of our settings and everything downloaded. So if you want to trace along to the C programs file to VS Codium. A lot of the stuff we do in Robotic, we're also working in the background with Python coding to make it all work. That's kind of the backbone of this software, and it's very handy for us since we have a lot of students that have some Python coding experience, so it's a handy tool for them to use as well. All right. So pass it on. So then once you have your, if you were able to open up VS Codium, or even any other Python program, you're going to load your Robotic folder, or go into the Robotic folder in your program files. So in that C program files, Robotic, you're going to be having a file that contains Python script to import settings. This is just going to be a quick way that we can get all of our settings logged in. It's not absolutely necessary, but it's going to help ease your way in if you're using Robotic for the first time. Some of the initial settings are a little counterintuitive to first timers, and this just makes the process a little bit easier on everybody. And yeah, we can run this program through VS Codium or any other Python editor that you have available. Let's see. And then yes, once you're set, you can select the Robotic settings import. And then in that zip file that you downloaded, there's going to be a file called robotic settings.zip. That's the file you're going to select after you've run your import program. And don't worry if you're not able to get this in time. This is just going to be something minor that's going to help you partially with visuals and partially with controls. But you should still be able to do all the things you need to do, even if you don't have these settings loaded right away. All right. So now you should be able to open Robotic if you have those settings loaded. And just a quick check that'll be able to make sure if it has loaded and taken, you'll be able to open up Robotic. Then you'll be able to go to your, in order to confirm that those settings transferred, you can go to the very top of your screen to the Tools tab, and then you can select options from that Tools dropdown. It's going to show a pop-up window similar to this. You should notice that your Python interpreter, Python editor are all set to those same things. Should be using the native Python on Robotic, the Python embedded, and then it should be using VS Codium as your Python editor. Those are just some quick keys to tell you. And also here I have the dark theme selected for the background. You'll notice that it's turned black instead of white, as it would be if you just opened Robotic normally. These are just small things that we have set up, but aren't going to affect our ability to do some of this programming right away. All right. So now if you were able to check that or not, we're still able to be working on our programming right away. So stepping in right away, we already have a 3D model of the cell created, and we have geometry of every piece of equipment we're going to be using in this cell. So we have our individual robots, their mountings, and then the individual pieces that we're going to be using in the cell. In this cell, there's a bandsaw that's used to cut off, say, gates and risers from raw castings, as well as a grinding wheel and grinding belt for taking down rough edges or easily accessible surfaces. So all this stuff has already been loaded either from somebody modeling up a piece of equipment, or in the case of pretty much everything in this cell, we have files of every single piece of equipment given to us by the manufacturers as a basic 3D CAD model. So if you go to Robotic and select File and Open, you can open the downloaded station that you should have. So you should have demo station handling.rdk available to open. If you open that up, you should get something appearing like this. So this is just a basic cell, very similar to one we have on campus that we use a 2-robot setup to work on. So in this case, we just have one half of those robots. That white Kawasaki robot you'll see sitting there with a gripper in it, with a pair of gripper jaws. And you should be able to see everything else similarly along the top and on the side. On the left of your screen, you're going to notice there's a bunch of different things that have already been filled in. This is our basically programming tree. So it has all the details that your robot would know itself, or that you're going to need to work with the simulation itself. You'll see a bunch of little triads for part frames or locations, as well as little objects that are different pieces of equipment throughout the cell. And as well, you'll also be able to see across the top, we have our basic toolbar, and then a bunch of icons that are going to be some of the common tools we'll be using as we're making our robotic cell and using each individual piece of equipment. All right. So to start out, as I mentioned, we have a bunch of models of our piece of equipment already made up with 3D CAD models of every single piece. In this case, they're all different step files, and then when we put it in this cell, what we had actually had done was a bunch of student employees had taken measurements to tell us where each piece of equipment was right off the bat. Now, that can get you pretty close, but it's not going to be close enough for a robot. The robot is going to need a little bit more accuracy, especially when we're doing some of the finer operations around finishing, where we're going to get very close to a part and we'll need to know very close and accurately where our robot is, where our part is, and where all of our tools are that we're working on it with. So to go from this, we're going to have to start taking live data from our robot cell and not necessarily relying on some of those measurements we were able to take in the field in our cell itself. So if I advance forward, so in this cell, you saw there was a pedestal there for a second robot. In this case, this cell works with two robot setup that are using a common turntable. In this case, we're going to be actually using that turntable because that's going to be our most common piece of equipment. Basically, just the workaround we'll be using, because it's going to keep things from getting confusing one robot to another. We're going to start by locating that Kawasaki robot that we have placed in the cell. So we're going to locate that robot relative to the turntable base in a more accurate fashion. To do this, we just did a simple locate frame process on that Kawasaki robot. Many robots have this setup. You'll either take 3 or 4 points, usually in a right angle, that are going to locate where a frame or a triad of location data are in space. In this case, we did it in a pattern on our turntable, right on the turntable itself facing our second robot. So this was already set up because that robot is the one that controls that turntable directly and has the control of that turntable as a 7th axis. In this case, we are able to pull from our cell right now. We can actually locate by selecting our Kawasaki base from the tree on the left, be able to see where it is currently. And by hitting our drop down of reference position with respect to, we can see it's related to our turntable base. If you select that option and go down to turntable base, you'll see where it is in space relative to it. However, this is not quite where it is in real life. So when we took our Kawasaki robot and found that exact same turntable base location in real life using a frame setup, we were able to see that it was actually located in this location. So it's a little bit off from where we'd expect it previously. However, we can still use these coordinates to relate it to our robot. In this way, we actually are able to relate it in reverse, because the robot found those 3 coordinates of the frame with respect to itself. We can then now relate the frame of that turntable base to our Kawasaki robot. So we're going to transfer it over in the fashion you see on the right. If you're looking at the example slide that you had set up before of our cell, you can actually do this in reverse simply by selecting the turntable base frame, and then by opening that turntable base frame, you can look at its position with respect to that Kawasaki base. That's going to be the location that base is, or that's going to be the same location that those 3 coordinates we have actually is. And then by using that, we're actually able to move our robot relative to it to get it to that new setup of 3 angles. Just because our 2 frames, the base frame of the robot and the base frame of that turntable, are not pointed in the same direction. So our X, Y, and Z coordinates are not going to be in the same locations as they are with respect to each other. So yeah, if you want to get it located correctly to where it is in real life, we're just going to have to copy down our location data similar to the box you see on the right for the Kawasaki base. All right, so now we have our gripper robot located. Now we're going to locate all the tools that robot's going to use, and we'll want the robot itself to locate these parts. Because when we're entering all of this data to make new programs into that robot, it's going to be able to find some of those locations by itself. However, when we give the robot raw coordinate data by itself, the robot is not going to be as accurate as if it was going to a position that it already knew. So in this case, we're using the frame that we're actually teaching with the robot to get us a far more accurate position to that robot than we would be if we just gave it frame data. A robot is going to be very repeatable when it's doing each of its cycles. However, giving it just new information on where to land, it's going to drift far further than if it was just repeating a cycle over and over. In this case, we're going to locate our combo frame. So in this case, that's our combination grinding wheel and grinding belt. You'll see to the bottom of the robot in gray. In this case, we'll start with our grinding wheel. And in this case, since that grinding wheel is located relative to its bottom, where its base frame is, we'll actually want to locate it relative to the location we're going to be doing work with that robot. So in this case, it's going to be our combo frame target, which we have already on the robot. So if you go further, you can then select that belt TCP. So the combo frame has two TCPs, or tool center points, basically locations the robot's going to use to perform different tasks. Either it's going to be using the belt for rapid removal of material, or it's going to be using the grinding wheel to do a little finer finishing and slower removal of material. In this case, since we already know where that belt location is that we're using with the robot, since we taught it that frame in real life, we're going to be using that to locate our robot. In this case, you're going to, in order to do this, we're going to actually have to change how our robot is organized. In this case, we have to move a frame away from another frame. So when working with Robotic or many other offline programming softwares, you're going to have something called a frame or some sort of reference frame for your objects, just where they're located in space and how they're pointed in space or oriented in space. This can be represented by a lot of different ways. If you look at the box on the bottom of the slide, you'll notice it's got X, Y, Z, and then something called ROT, Z, Y prime, and then Z double prime. This is what we would call, so we have our X, Y, Z coordinate, and we have something called an Euler angle. This varies robot brand to robot brand, but it's basically telling us how are we going to represent where this thing is pointing in space. For our purposes, since we're using the frame taught by that robot, we're going to keep everything taught in the same Euler angles that we'd use for the Kawasaki robot. So we're going to be using that. You can see from the list, Adept, Kamau, and Kawasaki from the list. So basically, in order to set up our frame, we've got to drag it out from under the frame it's using right now. To do that, we're just going to change the support. So in this case, our belt TCP, and we're going to change that support to some other frame. In this case, we're going to use U-frame 2. So if you shift and then drag belt TCP T, you can drag it onto user frame 2, or you can right click on the part on belt TCP T and then select change support and then select user frame 2 or U frame 2. And then we will land it there. That way it's no longer dependent upon where that robot is, where that combo head machine is located. Once we shifted that, we can actually now shift our combo frame underneath of it. So what we'll do is we will shift and drag our hold shift and drag our combo frame target and drag it on top of our belt TCPT. That way they're stacked on top of each other, where now our actual belt itself is relating to where the target frame is for that wheel. So it's some of the juggling you can do when moving parts around to get things organized. In this case, it can also get out of hand very quickly because you are relating parts to each other. When you are dragging and dropping frames relative to each other, you are basically telling something to relate itself to something else in the way it was related before. So say our belt was 10 inches above an object and 3 degrees to the right. Now, whatever object is dragged onto, it's going to be 10 inches above and 3 degrees to the right of that new object. So it can very rapidly shift where things are in space. And we'll actually take advantage of this in future workshops. We're actually able to use some of that knowledge to our own advantage instead of in ways to trip us up. But for now, we can actually shift where that belt TCP T is in our cell to where we actually found it in real life with our gripper robot. So what we're going to do is we're going to click on our belt TCP T frame, and then we're going to select our reference position with respect to our Kawasaki base. And then we can enter the coordinates that we have listed down here to get our piece of equipment related relative to that base. You'll just simply select that dropdown of reference with position respect to change it from user frame 2 to the Kawasaki base. I'll give you guys a second to get through that. It can be a little bit of a step to run through all of these things for the first time.
Is this going to be recorded and available for us?
This was being recorded and will be available to review later.
Okay, yeah, I'm way behind.
Yeah, there's quite a lot to go at once, and software setup, while it's nice to have, it's not going to change how you're going to be able to work this cell to your advantage. And a lot of this very first lesson is just going to be learning some of the basics to get things set up and squared away to start. And that's what we're going to start getting into a little bit more specific into, say, how we're going to use this to make actual finishing programs, how this sort of offline programming is useful to making different setups work much faster than if we had to teach it by hand with a teach pendant every time. But yeah, we'll be getting beyond that, and this will be recorded for later reviewing. All right. All right. So now that we've done that with our first piece of equipment used by that Kawasaki, we can now use that for our second piece of equipment. So in this case, we're using it with our bandsaw. In this case, we're going to do that same thing. We're going to shift and drag our cut TCP frame out from under the cut saw and place it on top of that user frame 2. And then we'll shift and drag the cut TCP on top of, or sorry, shift and drag cut saw on top of cut TCP. That way it'll be dependent on the other one, and we can just move our entire object as we remove it relative to the robot. It's all about using kind of what do we know on the robot versus what do we know in our model or our digital representation of this piece of equipment. Since we have these models from our manufacturers, we can know the location of different parts and pieces on that piece of equipment with relative certainty, more so than we could say know where it is located in the cell with the accuracy of just the hand measurements we've made in the past. All right. But once you have that cut saw dragged out and then our cut TCP placed back underneath, we're going to shift our coordinates to match the box you see on the right. So it's located with respect to our robot base. So whenever we're teaching with our robot a new frame in space, that representation is going to be laid out with respect to the base of the robot. Similar to, say, other robots where you're teaching a new frame or a new work object or whatever language a different robot brand uses, it'll usually be represented with respect to the base of that robot or the home frame of that robot. All right, just to check in, see where you guys should be if you're following along. This is not going to be critical, so the piece of equipment will now be located roughly where they are in the cell and how we're going to be using them. But this won't be absolutely necessary for the steps going forward. It's just going to be a step you would have to do if you were setting up your own cell to be used with offline programming. And this is even something that, say you were purchasing a cell like this from an integrator, they would be able to provide you with some of this information as well to build yours right off the bat much faster. All right. So yeah, we should be able to see our belt TCP and combo frame and our cut TCP and cut saw stacked just a little differently than they used to be. All right, now move forward to, now that we have our cell set up, we are going to start shifting in the part we're going to be working on. In this case, we have a pretty simple casting, just a square plate with a round boss on the top with a riser feeding that round boss. Kind of a simple shape, but we can show you some of the more powerful tools we can work with as we move forward with this part. However, just having the part is not necessarily enough. So we have this part, we have 3D CAD model for this part in this simplified state. However, we can make our lives a little bit easier on ourselves if we do some work with our model beforehand. Right now, you guys have a pair of downloaded step files of both of these parts, which already have this work done to them. This is just some of the stuff you'd want to work on before you had that part located in the cell. And this is just to make things easier for how we're going to locate these parts with a robot and then relate that information into our offline programming cell. So in this case, say here we have one of the two models, the completely clean and defeatured casting of how we would want it. We are going to want to locate our frame in such a way that our robot can easily find it Or in the case where either you're, say, teaching this by hand or say fitting it up against stops on a fixture, we'll be able to locate it repeatably every time based off that. In this case, we're going to move our triad origin to the top left corner on the top of the part. That way, either, if you're using a robot for a lot of repeated setups and you have, say, a vision system, there's very, very good algorithms in place on a lot of vision software to locate parts, or at least locate a corner feature on a part. So it's a very handy way you can locate parts in space automatically, or you can do kind of the old-fashioned way of using a pointer tool on a robot to pick out 3 points and create a reference frame on the surface. Either way, you'll be able to get this point much faster if we are already preloaded into the cell with where this place will be located on our physical part. So after we've located that origin to the location we want with our z-axis pointing straight up from the surface of the part, up the same direction as our little riser there, we can save it out as a step file. In this case, we're just saving as a step file because it's one of the ones that works most friendly with our offline programming software. In this case, you could save it step 203, step 214. And there's a few other varieties that different programs will work with as well. In some cases, we can use stuff like a STP file or an IGES file as well. All right. So now that you have your two objects and they're already been prepped to put in the cell, we're going to do this kind of the simple way by simply dragging that file. So if you have it opened up in a File Explorer window, you can simply drag that step file and just drag and drop it onto part frame 5, which should be located in your tree on the left. It'll be under your turntable base as an option. And you can simply drag and drop that and locate it into the cell onto part frame 5. And this, in this case, is where we have it fixtured in our cell. It's located against a stop, or in this case, 2 stops in our cell. So we know where it's going to be located every time on this little fixture setup we have in our cell in real life. You'll see it appear on part frame 5, and it should be nested like you see there in the picture above where our part's located. And you can do the same thing with the second file. So you'll have both the clean and the completely raw casting with all of the plumbing and fixturing still left on it. This way they'll be located basically on top of each other, where one is nested inside the other. And if you rotate your view, you might see some flashing features, which notes that, 2 models are overlapping each other. So they're both located in the same spot. All right. And then if you were to open up your individual part that you just threw down, you should notice that it's all located at all zeros. Depending on how you import the part, RoboDK also will sometimes throw on a default offset by itself. So sometimes it'll be 100 millimeters in Y, just to be in a location that's easy for you to spot. In this case, we're going to want to set all our location to all zeros. That way it's located in the spot we expect with respect to that frame. And that's the frame we would teach either with a camera or with our robot, so we know where that part is every time we're working on it. Now we can just check in. Should be able to have your piece of equipment already located, and we should see our 2 castings laying on top of each other in the cell under part frame 5. And if you are able to wiggle your view around just a little bit, either by holding your middle mouse button or your left mouse button and jiggling around, you might be able to notice it's shifting in and out of color where those individual pieces are overlapping each other. All right. Anyways, now that we have our 2 different pieces, our 2 different work pieces already set out, we're going to do one final step to make sure everything is ready to start working in this cell and how we're going to be working with these robots and make sure we have a safe setup to work from, starting with our next lesson as well. To start, you're going to make a brand new program. So in these programs in RoboDK, they allow you to do several different things. Not only can you control motion, you can start looking to different pieces of equipment and say reading sensors or reading or sending digital inputs and outputs and control logics as well. In this case, we're just going to start by making a brand new program by selecting it from the toolbar on the top. So with our new program, we're going to make a initialization program. So this is kind of a good standard practice when you're working in your robot cell is to have some initial state you want to start from every time. That way, as things get off or you start working in the cell or you make a mistake, you're able to hit a safe reset point. All of our tools will be reset and all of our parts will be snapped back to their original locations, so that, say if we made a mistake or if we wanted to change something, we're easily able to go back to a point where we knew where everything was and all of our equipment was in a safe home position. In this case, we're going to start by making our initialization for our gripper robot. So the way we can do that to start is we're going to actually select our new program and we're just going to rename it. When we rename it, you can either double click on that program or right click and then select rename. Also by hitting the F2 button. But if you select that program, we're just going to rename it to something like gripper init in this case. So this just tells us basic information. So this is my gripper robot and it's the initialization step. In this case, because this isn't a gripper robot, we're going to do one extra thing where we're resetting objects with respect to our robot. But in this case, we're going to be doing this all over our Kawasaki robot. If you had multiple robots in the cell, you can also double check to make sure we're doing this correctly by hovering over your robot drop-down option and making sure it's selecting that Kawasaki robot. All right, there we go. All right, so now that we have our robot, we're going to make sure we're working with the exact pieces of equipment we want. So the way we're going to do that is we're going to start with our reference frame of how we're going to work with our robot. We're going to select our Kawasaki 210L base in the tree. If you right click on that, you should have the option to select our, excuse me, should have the option to select the active frame. If you right click on that, you should be set to the Kawasaki gripper to the 210 base. In that same way, you can select the pinch gripper assembly from the tree and select that as the active tool. They should both have checkboxes, so you'll know that those are the active tools in our cell. This is just telling the robot, here's the robot we're working with, here's where everything that we're going to be feeding it information-wise is relative to, and what tool is going to be doing all this work. And if you right-click on our program, we can add our instruction and select Set Reference Frame, Instruction, and also our Set Tool Instruction. So in this case, our setting a reference frame should automatically be our Kawasaki 210 base option. So if you need to edit it, you can just double click on that set reference instruction that you'd have made by clicking that add instruction. And then also you can set your reference frame tool frame instruction by selecting that new tool from the set tool instruction from that list and selecting pinch gripper assembly. That way we have our tools that we're going to be using for our initialization. Give you guys just a second. There's a little bit stacked up there to do. And don't worry if this doesn't come in automatically. The next step we're going to do is actually going to inherently bring some of this with it. So in this case, we're going to get a home position. So kind of the quick way to do this, with this robot, we have a pre-built-in home position. In this case, if you double click on the robot itself, either sitting there in the cell on its 3D model or on it from the tree, you'll get a pop-up that looks like the box on the right. That shows where our robot is. There's a lot of information here. It's basically just relaying where our robot is in space, where it is relative to the frame that's active, and where our tool is. It's located with a lot of dense information, but for now, we don't need to worry about it so much. The only thing we really want to hit on here is near the bottom here is the joint axis jog option. And then to the right, there's a home button. If you just hit the home button, that's going to snap our robot to the home position we'll be using to start out these programs, where our robot is stowed safely away from all of our tools, all of our different pieces of equipment, and is out of the reach of any people if we ever had to come into the cell to manually fix something. In this case, you'll hit the home button, and then we'll select the target button from the top toolboard on our RoboDK cell. You'll see a new target icon pop up in your under your Kawasaki 210L reference frame in the tree. That's how you'll know it's worked. So going forward, we're actually going to select that new target that just popped in. All we're going to do for here is just rename it. If you right click on it and then do the same thing we did before for the program, we'll just rename it to home. Since this is going to be an object we're going to be using quite a few times, whether it be, you know, we want to get to a safe space, or we want to say after an operation, we want to go back to a home position so we know where we're going to go for our next operation. In this case, we'll rename it. Then the next thing we're going to do is if we right click on that home target again, we're going to go from that drop down and select joint target. So this is just to make our setup as simple as possible. When a robot gets information of, you know, where it is in space, it's presented in a few different ways, but the two big ones we can use are either XYZ WPR coordinates or joint information. So basically, at what angle are each of the joints on that robot located? So those joints can only be laid out in one specific way, so the robot will know exactly where it is every time when it's given a joint target. But a robot can also reach an XYZ position in space in a number of different ways with all of its joints. So in this case, since we want our home position to always be the same, always make sure our robot's going back in the same way, we're going to change that target to a joint target. So a robot is always going to be fed information of where each of its joints should be in space. In this case, yeah, we're going to select joint target from our home position. All right. And now that we have that target made, what we're going to do is we're going to click on, with that new point, we're going to first click on our gripper initialization. Then you're going to hold Control and click on that new home target that we just made. That way we'll have them both selected. And then we're going to hit the joint move option. So it'll be up on your top toolbar in that little squiggly line pattern next to the new program button. This is just telling it to do a joint move. So when you have a robot, it's got a few different ways that it can move to do different operations, or it's simply how the information is going to be relayed to the robot and how it's going to move. A joint move is one of the two basic ones. It's basically telling the robot to move all of its joints all at once to get to some other joint configuration all at once with all the joints stopping at the same time. So if one joint is further away from that than the other, it's going to move faster. And if one joint is closer, it's going to move slower. So they all arrive at the same spot at the same time. It's a very simple optimization program. So the robot is able to do this regardless of where it is. And you're able to feed this regardless of where you want it. However, it moves a little unpredictably, just simply because you have so many joints and arms moving all at once. The other option you'll see on the top of that bar is a linear movement. This is going to move the robot from one point to another in a straight line and potentially rotating orientation as it goes. So this one's just a slightly more complicated program. And since the way the robot moves, it is basically just solving a large mathematical equation. Sometimes when it moves in a straight line, it's going to come across a way where multiple different joints can cause it to get to the same place by doing different things. And it's kind of an unsolvable problem for the robot. So you might get some issue that's called a singularity. In this case, we don't want to have any issues when we're trying to get back to our home position. So we're just going to leave it at a joint movement this time. So if you hit that joint movement icon, your toolbar, it should pop up in your gripper program and look like the little, in the tree, it should look like the little drop down just below our toolbar there, you'll see on the right. All right. So now we get to go into a little bit more details of how we're going to move this robot. So we've already told it, you know, we want to move to our home position to get away safely. We want our movement to be the joint movement, so we know exactly where it is with all of our joints, and we don't have to run any issues along the way in terms of getting screwed up in terms of how it's going to move there. Our next way we're going to have to tell that robot how to move, though, is how it's going to be moving in terms of speed and in terms of how close it's going to stop to our target. These two things are called speed, and they're also called rounding. We're going to start by setting a speed. So if you right click on your J move that you just made, you should be able to select the add instruction option and then the set speed instruction. When you select this, you should get a pop-up that's asking you a whole bunch of different things, like if you want to do this as joint acceleration, joint speed, or linear acceleration and linear speed. In this case, we just want to have a linear speed setting. Not going to worry about acceleration for this one. We'll leave it to the default of what the robot's already set at, just because how we're going to arrive at our location doesn't matter since we're not interacting with anything along the way. So we're just going to set our speed to 500, which is a not crazy fast movement for that robot, but it will get there at a reasonable rate away from whatever we're working on. Yes, not as fast as that robot can move, but at a reasonable rate. Beyond that, we're also going to have to set a rounding instruction. So robots can move in a variety of different ways. Rounding determines basically how wide of an arc that robot's going to swing through and each motion to get to a target. And the kind of idea of this is the wider that arc is, the faster the robot can move through that motion. But your path is not going to be quite what you expect if you're giving it that wider arc. Most motions that you're doing, say, away from a part or not doing any actual operation to affect the object you're holding or working on, can be done with a little bit of rounding value just to keep the speeds high and allow that motion to be completed smoothly. However, when we're coming to this home position, we're going to want to have it do a fine movement. So in this case, it's going to come to that spot we told it to go to, and it's going to pause there for a brief second. On different robots, this varies in terminology and your little wait period. But in this case, in Robotic, the way we tell it to do a fine movement is by setting a -1. So what you're going to do is you're going to right click on that J move and you're going to select add instruction and you're going to set a rounding instruction. And in that new pop-up, you'll just leave it as a -1. In Robotic, this just means a fine movement. Instead of telling it, say, a number, like if you were to tell it 10, then it would set a rounding arc that it's going to round off any corner of movement to a 10mm round circle. In this case, we want it to stop exactly where we want it to be, and it's not going to make any other stops along the way. So we're going to leave it as a -1 or a fine movement. All right. Now we have how that motion is going to happen. Now we've got to control some of the other pieces of equipment that this cell is going to be working with. So in this case, for our initialization of the gripper robot, we've got to control how all the objects in the cell are going to change when we use the gripper. So when we're using the gripper in the simulation, it's going to physically pick up that object, so we know where that object is relative to our gripper and how it's going to be moving around our cell as we're working. In this case, you're going to want to select the event instruction, which is going to include that little circle with arrows you'll see on the top of the toolbar. It's going to give you a variety of options, but just go from your action dropdown. You're going to select set position, object position, absolute. And then we're going to have a whole bunch of options. But what we're going to do in this case is we want to set everything that that robot is going to interact with the gripper, at least when it's grabbing, to be able to be reset. So you're going to select your base plate, your rails, your stop, and our cutoff test part. So in this case, we're just all of our fixturing and then our regular cutoff test part that has all of our rigging and parts attached. In the next lesson, I'll show you why we aren't going to grab our cutoff test part clean, so the one that's got all the gating removed. But for now, we're just going to select this option. And these are all going to be objects that when we reset the cell, they're going to snap right back to where we have them set right at this moment. So that way, when we're running our simulation, if we ever get off, we can just select this reset and we'll be ready to start again and go again from the beginning. If we have to re-grab our object, that's just the next step we'll have to do. All right. So you should be able to have that selected. Now that was taking care of the simulation of how it's going to be reset. Now we need to take care of how our tools are going to be operated in this cell. In this case, we are actually operating our set of jaws with digital inputs and outputs. In this case, we're using a digital output signal that's telling that clamp to close. Just controlling a little pneumatic valve that's telling it to send pressure to the jaws to either open or to close. In order to set this up in our Robo-DK simulation, you're just going to select the I/O button, which is right next to that simulation event icon as well. In this case, you're going to select the gripper initialization program. Then you select that I/O icon. You should be able to get a pop-up. You're going to actually get a new symbol that will show up in your tree. If you select that symbol and go to edit, you're going to get this little pop-up you see here with the I/O name and it's your type of I/O. In this case, it's a digital output because we're telling it what to do. That tool is being told what to do by the robot. So we're just going to set that to IO number 9, which is the signal that is running that gripper. And we're going to set it to 0, which is the JAWS open command. A lot of different tools can be operated in this fashion. We're going to come across a few different tools later on as we're programming the cell for different finishing operations that are run in a similar fashion. And then also we're going to be looking for stuff where we're going to be looking for an analog input not analog, digital input that's going to tell us when a certain action should be performed or when an action has been performed and when we want to continue. All right, so now that we have that, because we have our gripper action, we're also going to want to include a wait. So the basic idea of this is that whenever we're running this gripper and to open or close, it's not an instantaneous action. And when we're sending signals to the robot, it has a set schedule of how different signals are activated and how it interacts with motion. So if we were to send a signal just straight to it while it's moving, it's actually going to send that signal mid-motion. In this case, it may open up with a object in its jaws, and it's going to say, while it's moving, toss that object and not say, just let it go and then move away, which is what we would actually want. So we're going to add a wait command, which is that little hourglass icon you'll see in your top toolbar. In this case, you'll add it just after your IO setting, and then we're just going to set for 3,000 milliseconds from that option, which is just going to be 3 seconds to open those jaws, which is more than enough time for the jaws to activate. But in this case, we want to make sure that nothing's going to go wrong with our first initial setup, and then we can go from that. We're not going for speed when we're doing this initialization step. All right. This will be the final check-in for this, just to make sure where everybody's at. Your cell will look basically the same as it was before, but you're going to have this little gripper initialization program, which is basically going to be our way to reset our cell to get back to a safe space whenever we need, or say if ever we make a mistake and we want to go back to some point where we knew everything was the way we wanted it, which is very possible as we're moving around and doing different things like grabbing and placing. Sometimes we'll get things just a little bit off or grab it in a way that we don't expect. All right. All right. That's it for this one for today, for this workshop for today. As we go into the next lesson, we're going to actually start working now that we have our gripper set up, we have our program ready. I'm going to start to show you some of the stuff we can do with our robot just by grabbing an object and bringing it to different tools. So this kind of relates to similar ways that operators would be doing this right now in foundries across the world, where they're going to be using individual tools and just holding and pushing an object in. It kind of relates in a similar fashion, but we're going to have a different idea of a control scheme and how we're going to tell that robot how it's going to relate to its space. That'll be coming up in the next lesson. For right now, I just want to open up the floor to anybody who has any questions about any of the material covered today. If things have gotten off, or if you have something beyond, anything that's gone horribly wrong with your cell or anything in it. All right. Anybody have any questions? All right. I don't have anything from anybody. Oh,
we're going to get the video of this before the next session, right? Because I get lost in the.
Yeah, I know it's very easy to get lost in the chain of events.
Yes.
I can get you we'll get the video sent out, so you'll be able to see everything that we've run through today, and you'll be able to take it back step by step and be able to at least see some of these slides where each of those different operations are and how things should look, at least by the end. Correct. Yeah, unless something has gone terribly wrong. I know when you're starting to move objects around, especially with shifting the frames around, you can start getting some really wacky shapes. My recommendation is that you would save before you try a frame shift on your own, just because you can very quickly get things out of whack in such a way that the undo button doesn't fix what you did wrong. It's one of the disadvantages, say, to this program. Other offline programming languages have it a little different, but they work in a different fashion as well. And just to keep it out there, there are definitely a lot of different offline programming systems that you can work with, either related to your robot manufacturer or ones that work with a variety of robots as well. Any other questions? hopefully hopefully as we go forward, this will get a little bit more relevant. Today was a nice day to set up everything you're gonna be working with. Some of the stuff you work with in robotics, you're just gonna wanna have a firm base to start from and a safe spot to go back to make sure that any mistakes are easily recoverable and that you have a baseline that you know and expect, and get a little bit more comfortable with how your robot's gonna operate. All right, and if that's all the questions I have for today, thank you all for stopping in. I look forward to talking with all of you guys on the next workshop session. All right. Thank you guys.